Okay, hello everybody. My name is Mansour Khosravi. I am with Illinois State Geological Survey. I am reservoir geologist, and in this webinar, I wanted to talk about carbonate reservoirs. In this presentation, we will review the carbonates components, also carbonate factories. And after that, we will talk about the classification of carbonate rocks. Also, we will tweak a little about the geometry of the carbonate depositional environment. And finally, we will talk about the Diogenesis and the effect of the Diogenesis on carbonate rocks. So the first question is, what is the difference between carbonate and clastics? Can we apply those technique that we use for siliciclastic to carbonates or not? Actually, the main or predominantly difference between the carbonates and clastic is the carbonate are composed of the sediments or fragments that generated within the basin, but the clastic are generated from the fragment of pre-existing rocks, same as igneous rock, metamorphic rocks, or previous sedimentary rocks. But actually, the carbonate rocks differ from the clastic because they are more susceptible to diagenetic modifications. But actually, we can use those interpretation techniques that applied for clastic to the carbonate as well. If you look at this image, you can see different depositional environment, different system. For example, at the upper part or upper basin, we have alluvial system. We have fluvial for siliciclastic. We have aeolian systems. But mostly the carbonate are generated within the basin, for example, in the shelf area, in the slopes, or in the deep marine. We have, actually in the leucosterine system, we have also the carbonates, but they are not important as much as the marine system. If we look at these images, we can, at the upper part, we can see the distribution of reservoir rocks or siliciclastic reservoir. In the world, we can see in different area, in different latitude, we can see the siliciclastic reservoir. But if you look at the carbonate reservoir, we can see the carbonate reservoir just in a special latitude, but they are very important. Look at this part, for example. This part, we have huge siliciclastic reservoir, especially in the Middle East. But you can see also we have those carbonate reservoir in Middle East as well, or in the North America, we have siliciclastic, and also we have carbonate. So they are very important for us to learn how to describe them and how to interpret the diagenetic systems that affect those type of rocks. Another question is, are carbonate reservoirs difficult to study? Actually, they are not difficult to study, but they require different knowledge to study and interpret the carbonate reservoirs. So we need a different type of knowledge to compare to siliciclastic, to interpret those and explore those effects, those diagenetic effects, to learn about this type of rock. And what is the main challenges in developing carbonate reservoirs? The main challenges are heterogeneous nature of the carbonate reservoir. And I will talk about this item in next slide, Diogenesis and also rock fabrics. For example, look at these two thin section images. One at the left, you can see shadow of bioclast, the shadow of bioclast, and it's stained by epoxy. So you can see the porosity with blue color here. And in this image also, you can see the porosities. But if you look at the pore throughout sizes, you can see different pore throughout sizes. This is a bioclast grainstone, but look at the pore throughout. In this part, they are very thin. In this part, they are very coarse. But look at this image here. It's a bioclast grainstone. But if you change, if you replace these oids or bioclast with quartz, and you can say that this is a sandstone, you cannot see any differences between a sandstone or quartz arenite with this type of rock. But actually in this rock, it's much different with siliciclastic because we have different pore throughout sizes. Okay, in this image, you can see the carbonate precipitations. We have, in the marine system, we have two types of precipitations. One of them is abiotic and one of them is biotic. Abiotic is actually when in the tropical marine surfaces, when they are supersaturated with carbonates, after removal of CO2 from the surface by agitation, by photosynthesis, or by warming, this type of chemical reaction permit to have this type of precipitation of the carbonate in the marine system. But most of the precipitations actually related to biotic because they generated from skeletal grains, for example, some bivalves, some reef system, and they generated from them. But we have another type that induced by biotically, and they're induced by their activation or reaction of the organism, for example, the microbial system. If you will look at this image at the right side, in this graph here, we can see the sea level fluctuations. And you can see that in the marine system, because we have about over 90% of the carbonate are deposited in the marine system, but you can see also the sea level fluctuations here. For some period of time that the sea level goes up or reach to highest stand, we have high Mg calcite or carbonate factories, but when sea level goes down, we have also carbonate factories, but actually in this part, when sea level goes up, we have high production of the carbonate system or low Mg calcite. When sea level goes up and reach to highest stand, we have low Mg calcite. When sea level goes down, we have aragonite or high Mg calcite. But we know that these two type of mineral or these two type of calcite are unstable. And after a short period, they will convert to either low Mg calcite or dolomite. Yeah, but if we compare this type of sea level fluctuations with actually siliciclastic fluctuation system, for us, for carbonate, when sea level goes up, we have high production. But in siliciclastic, when sea level goes down, those actually sequences are very important because they can, I am talking about hydrocarbon systems, because on that part in the basin, we have lower stand system tracks when similar to lower stand wedge, lower stand fans, and we have siliciclastic with porosity, and they are that very important for us. But in the carbonate, when the sea level goes up and reach to highest stand, they are very important for us. In the next slide also, I will talk about this part again. Okay, what's the main component of the carbonate? The carbonate are composed of three components: the grains, the cement, and matrix. The grains are composed of non-skeletal grains, same as ooid, piezoid, oncoid, peloid, and also class. Most of them are intraclass, but we have some grains of some type of quartz grain that we say that they are extra class, and we have skeletal grains. We have also cement, the cement that they are porphyrin of the porosities, and we have matrix. So at first, let's look at the non-skeletal grains. They are ooid, they are spherical, actually, components, and the size of less than 2 millimeter, and they are very important for us because they show the energy of the environment. When we have ooids, most of the time we have high energy environment. Also, we have non-skeletal grain as oncoid. Oncoid are similar to ooids, but actually they created by, if you remember that we showed that something that in the biotically induced precipitations, they are one of those, and they created by cyanobacteria and also the carbonite system, but they shows very calm environment. The other non-skeletal grain is aggregate or grapestone. You can see in this image a grapestone. They are composed of some non-skeletal or skeletal grains that connected with each other with micrite, and also the clasts. Clasts are very important for us because they show us the energy of environment, and also when we have, for example, intraclast grainstone, it shows a channel system for us. And as a carbonate reservoir geologist, it's very important to find the area that has a high energy, because if we have a high energy environment, maybe we should have some type of porosity and permeability. Another non-skeletal grains are peloid, oncoid again, and piezoid. And the peloid shows not very high in high energy environment. They shows leeward of the, for example, lagoon toward also the barrier or toward the tidal flat. But for piezoid and oncoid, most of the time, they actually shows a lower energy environment. We have skeletal grains, same as foraminifers, same as sponge, same as pelagic sediment, also reefs, bryozoans, also brachiopod and gastropod, and also cyanobacteria or microbes. If you look at these two images, in this part, in the lower part, this is our basin. In this part, we have shoal system. Behind the shoal, we have lagunal system, and at the other part, we have supratidal. In the lagoon system, we can see some type of gastropod, but the energy is moderate to low. But in the shoal system, we can see the high energy environment with oids and also reef system. In the basin system, we have a fragment, at the slope, we have some fragment of a skeletal system, and also in the deep marine system, we have some pelagic pelagic fossils. But in the supratidal, we can see in the arid condition, we can see some type of evaporites, and also the dolomitization, or in this part, sometimes in this part also we can see some plate greenstone, because this part of the intertidal has a higher energy, but toward the upper part we have a low energy. If we compare the energy system or wave or current to the depositional system, you can see from the intertidal to the shoal system, the energy or wave system or current system goes up. But in this part, for example, lagoonal system, the energy goes down. So when the energy goes down, we shouldn't see too much actually porosity, but in this part, in the shoal system, we can see the energy and also cementation, the greenstones, reef system with porosity. The carbonate matrix, actually the matrix is same as mud, but they are carbonate mud. They are not same as, for example, siliciclastic muds. But the size of the lime mud are different based on different categories. For example, some people say that the size of the mud is less than 6 micron, but some people say that it's less than 4 micron. But the mud, it's generated by different processes. For example, mechanical disaggregation of the carbonate grains, bioerosion, chemical or chemical precipitations, or deposition on the tidal flats. So we have different environment and different processes to create mud. Let's look at this image that shows the carbonate factories. We have 3 different carbonate factories. Most of the carbonate actually located in this part. This is the tropical carbonate factories. You can see they are actually dependent on the light and also the photosynthesis and also the agitation of the marine system. But most of the carbonate precipitation are located here, but we have some type of mud in the deep marine system, because they are not independent to the photic zone, or they are not independent. They are independent from the light. But in the cool water system, you can see from the surface to very high depth, we have carbonate system, and in the cool water system, we have some sort of skeletal grains or skeletal bivalves and etc. Okay, we have so many actually carbonate classification, but 2 of them are most accepted by geologists. One of them is from Dunham classification in 1962, and the other one is from Folk. So if you look at this image at the left side, you can see based on mud supported or grain supported, the Dunham categorized the carbonate rocks. For example, if a rock is mud supported, it means that most of the rock system contain mud, but with less than 10% grains, we say that this is mudstone or lime mudstone. If it is mud supported with over 10%, we can say that this is whackstone. If they are grain supported, but with mud or with cement, we say that this is packstone. But if we have just cement and grains, we can say that this is grainstone. He categorized all of the reef system or all of the component that bond together. He named those bondstone. And for dolomite, he mentioned that they are crystalline, actually grains. So he mentioned that this is dolomite. But after Dunham, Emery and Clavan actually just divided this part into 5 other categories. If we have, for example, in the slope of a depositional marine, if we have some sort of grains or rework grains of reef system, and if they are less than 10%, we say that they are float stone. If they are more than 10%, we say that they are roadstone. But if the organism act as a baffle, they are baffle stone. Act as a bind, they are bind stone, and act as a frame, for example, Rudy system, they are frame stones. But we have different carbonate classification. That's from Folk, 1962. And just these 2 classification are based on the texture of the carbonate system. If we have just a sprite or cement with grains, based on the type of the grains. For example, if we have intraclass, we say that intrasprite. If we have intraclass and micrite, we say intramicrite. If we have oids with cement, we say that oid sprite. But otherwise, if we have micrite instead of cement, we say micrite. But after that, he modified his classification to this classification. If you say that if we have 2/3 of lime mud matrix, if the rock mostly composed of lime matrix, and lime matrix is more than 2/3 of the rock component. So if you have just mud, we say that that's micrite or that's dismicrite. Dismicrite, they are actually frustrate porosity that filled with cement. And otherwise, so he used clay stone, sandy clay stone, or poorly washed biosprite, and etc. for those rocks. Let's look at some of those thin section and the name of those thin sections. For example, we have in this thin section, we have oids and we have cements, but you can see the roundness of the oids. So folk name is rounded O-sprite, but the Dunham name is oolitic grainstone. Here we can see that we have different foraminifers with different sizes. So folk name is unsorted biosprite, and Dunham name is mixed fossil grainstone. For this actually rock with just plate, they have the same sizes. The plate have the same sizes. So folk name is sorted plasprite, and Dunham name is plate grainstone. Another thin section, for example, that's packed because we have so many fossils here. The full name is Pag Biomicrite, and Donham name is Mixed Fossil Lime Whackstone. And here we can't see any fossil here. We can see just mud, and full name is Micrite, and Donham name is Lime Mudstone. Again, full name for this thin section is poorly washed biomicrite, because we have micrite here, we have cement here, and we have also bioclast here in these areas. So Donham name is bioclast packstone. And for this one is poorly washed biomicrite. We can see micrite here. We can say bioclast in this part. In this part, most of them are pelagic here. And Donham name is bioclast whackstone. Okay, let's look at right now the geometry of carbonate depositional environments. We have 3 or 4 depositional environments for in the marine system for carbonate. One of them is rim shelf. The rim shelf, the special character of rim shelf is the actually a slope of the this platform. The slope of this platform is between 1 to 90 degrees. In this system, we have a pronounced breaking slope from shallow marine to deep marine. And it's because of the presence of the reef system, or the actually the carbonate rocks or carbonate organism that catch up with the sea level, and they create huge factory of carbonate sediments. So if you look at this part from shelf margin to the basin, you can see in this part we have some sort of reef. In the slope we have some breccia debris flow, and also some type of packstone here, but the grains are very coarse. But toward the basin, the size of the layers and also the size of the grains decrease. Toward the lagoon, behind the shoal system or shelf margin, we have a lagoonal system, and it's very extensive part. And we have some sort of patch reef here. We have some sort of grainstone in this part and also in this part. But we have some sort of mud here. And at the upper part, we have the siliciclastic. We have some sort of the dolomitization. Here we have some sort of erosional systems. We have some sort of evaporite in this part. But for carbonate ramp, actually, just this figure is just schematic figure for carbonate ramp. But we know that the slope of the carbonate ramp, for example, we have the carbonate ramp in the Persian Gulf. So actually a slope of this system is less than 1 degree. So we don't have very extensive carbonate system here, but we have higher energy shoreline in this part, and toward the basin, actually the size of the layers and also we have also the fine organism or skeletal grains, but we have also a lagoonal system, but not extensive as the shelf system. Again, in this part, in the tidal flat, we have some sort of evaporite, and also we have some sort of dolomitization. And in most of the part in this region, we have some sort of oid grainstone, and we don't have any sort of the reef system. But in some part, we have some patch reef, not full reef in this area. Another type of platform are isolated platforms. This type of platform actually isolated in different parts, in different locations. For example, they are surrounded by deep marine, but depend to the wind, the direction of wind, we have different lithologies. For example, if this part is windward, in this part we can see the reef, and in this part we can see mostly the oid grainstone, but in the deeper part we can see the slumps, the slide, and also in this area we can see the sediment like the lagunal system. If we look at this image, and this is a carbonate factory, we have, based on the transgressive or high stand system track or lowest stand system or sea level, it's better to say the sea level fluctuation, we have different type of deposits. For example, at the start of creating a platform, if the sea level goes up, after a lag, the organism start to create carbonate sediments. After that, when the sea level goes up, the carbonate production goes up because they wanted to catch up, they wanted to get the light. So they produce actually carbonates here, and we have huge thickness of carbonates in this part, in the catch-up parts. But when the sea level stay at the same level, because of the carbonate production, we don't have accommodation as much as the sea level goes up. So we don't have accommodation. But in this part, the sediments try to prograde toward the basin, and we have prograde at the highest stand. We can see the progression of the sediment toward the basin. At the lowest stand, these sediments, actually the sea level goes down below the shelf break, and these sediments affected by, for example, the rivers, the rainfalls, and they will be leached, and also they create porosity for us. But we have some sheddings or some fans, because we have the river system, we have some fans of sediments or at the slope and also at the basin part. The last part of creating a basin is the sea level actually suddenly goes up and the platform drowned by the sediments. Okay, and this figure shows the evolution of a platform. Just don't suppose that if we have a ram system in other period of time, we should have a ram system. Sometimes in one area we have ram system, but after a period of time, this ram system changed to rim shelf. Look at this part. We have the ram system, actually a slope is less than 1 degree, but when the sea level suddenly goes down, we have prograde of the sediments over that. So because of that, right now we have the rim instead of the ram, we have rim shelf. And also in this system, at first we have the rim shelf, but because of the just slowly falling the sea level, after that, this rim shelf, platform actually changed to a ram system. If we wanted to see the positional sequences of a rim shelf, at first, if you look at this is open marine system, this is the sea level, and in this area, and this is the shelf system, in this area we should see the actually the reefs. Look at this part. At the sequence boundary, when sea level is here, in the sequence boundary, we have some type of erosion. And because the sea level is here, we have the position of the siliciclastic here, same as lower stand wedge and lower stand fans. But after that, when the sea level goes up, we have the condensation. So we have thin layer of carbonate, especially the pelagic system. They cover the sequence boundary and also the lowest stand system track. But in the highest stand, because of that keep up and catch up, we have reef system here, we have lagoonal system here, and we have debris flow here, and also progradation because of the high rising of this system. So we have some sort of shedding of the systems. So the sediment prograde toward the sea level. And again, we have the sequence boundary at the upper part. But for the RAM system, you can see that we have those type of sequences or system track over in this area, but you can see the deep is not as much as the rim shelf system, but we have those, for example, lower stand wedge, lower stand fan here. Again, we have the TSD here with thin layers, and again, very extensive, actually, the highest stand system track in this area. And again, we have the sequence boundary. And for the isolated platform, you can see in two sections. In this section, for example, we have lower stand wedge and lower stand fan here, lower stand wedge and lower stand fan here. In this part, we can see, because that's the direction of wind, we can see that the condensation here, and also in this part, we can see the highest stand system here, and also erosional system or sequence boundary at the upper part. Okay, let's look at the Diogenesis. What is the Diogenesis? The Diogenesis actually encompasses physical or chemical changes that affected the sediments after the deposition. But this period of time, this process actually longs toward at the starting of metamorphism. So it's between the chemical and physical changes between the sediment deposit to the metamorphism processes. We have different type of Diogenesis, or different, it's better to say different area for Diogenesis. One of them is for started at the seafloor, or we can say that marine Diogenesis, or in the area without, in the area actually far away from marine system. It means that meteoric Diogenesis, or at a high depth, or that we can say boreal system. So the Diogenesis system for us is very important, because actually they create porosity. As a reservoir geologist, as a carbonate sedimentologist, the porosity, permeability are very important for us, because we are looking for reservoirs. So because this type of process create cap rock for us, create also reservoir rocks, because of those processes, they are very important for us. We have different type of Diogenesis, for example, cementation, dissolution, replacement, recrystallization, dolomitization, microtization, and physical or chemical compactions. If you look at this schematic actually figure of the type of the Diogenesis in different depositional different environment. For example, in this part, you can see the meteoric weather zone because in this part, just some of the grains, some part of the grains or pore system filled with water, we have some different type of cementation, different type of dissolution, and below the water table, we can see also the different type of cement or dissolution. Also in the shallow burial system or intermediate burial system or deep burial system, we can see different type of texture, we can see different type of cementation, and also different type of carbonate regards to the cementation, the compaction, and etc. If you look at this graph, it shows that for most of the modern carbonate, especially for example for chalk or for reservoir rock, we have between 30 to 75% porosity. But because of the diagenetic effects, or because, for example, because of the cementation or compaction, for most of the carbonate rock, the porosity changes from this actually high porosity area to from 0 to 5% porosity. And for carbonate reservoir, it's between about 10% to 30% porosity. So let's at first look at the cementation. What is the cementation? We say that the precipitation of cement in carbonate is a major diagenetic process because it reduces the porosity. When the pore fluids are supersaturated with carbonate, actually they precipitate those cement on other areas. So because of that, we have different cementation. Let's look at some sort of cementation. For example, marine Diogenesis. The marine Diogenesis started from, let's look at again in this figure. That's marine Diogenesis started from here, when the sediment deposits, exactly after the sediment deposit. Because of that, it's a short period. And you can see that we can see different type of cement. For example, we can see some type of fibrous cement or some type of needle type cement or botryoid type of cement. In this figure, you can see this type of cement. So if you learn what is the type of cement, for example, in the marine system, in the meteoric system, it helps us to find the history of Diogenesis. And it actually assists you to find, for example, the positional sequences. After that, you can, as an exploration geologist, you can find the area with meteoric, for example, Diogenesis. After that, finding the system tracks in the sequence stratigraphy and finding those, for example, high stand system track with huge limestone and with higher porosity ranges in other area of the basin. So there are two types of the marine cements. And if we see this image, you can see in this meteoric Diogenesis, because especially in the Vada zone, the pore system of the carbonate are not fully actually saturated with water. we can see just at the contact of the grains, we can see some sort of cementation. But in the phreatic zone, it means that below the water table, we can, because the pore system actually filled with water, we can some type of blocky cement or isopachus, isopachus type of cement. Let's look at these two types. In this oid grain stone, you can see a Veda zone, a Veda cement here at the contact of the grain. But here, below that part, you can see the oid grain stone with blocky cement. It means that one of them, let me show, one of them is here, and one of them is located in this part. Okay, again, in the meteoric Diogenesis, because the water, because of the rainfalls, we have acidic water, we have some sort of leaching. You can see this gastropod. Most of the internal part of this gastropod leached by water. So we have porosity here, and also we have some type of aragonite at the edge, some sort of aragonite cement at the edge of this aragonite. That means that we have this actually deposited in a the diagenetic processes is meteoric Diogenesis process. So again, we have leaching here. For example, this oid grainstone, we can see very good moldy porosity here because of the leaching of the meteoric Diogenesis. And also here, you can see some sort of, for this bioclass grainstone, we can see some sort of vugs or also mold here, that we have porosity here. But another type of Diogenesis is biodiogenesis system is burial Diogenesis. Actually, this type of Diogenesis is important for us because it shows the compaction. It shows the two types of compaction. For example, the physical compaction or chemical compaction. And in this stage, most of the calcite change from the low, aragonite and high Mg calcite to low Mg calcite. So if we look at this one, for example, in this part, you can see the grains here, but because of the ductile character of the grains, you can see this convex and concave contacts of the grains because of the compaction, physical compaction. For brittle grains, we can see the fracture. Mostly in dolomite, we can see this type of fracture. And also, again, the contact, we can see the contact of the grain with compaction. But here we have some reaction, and after that, because of the compaction, we have chemical reaction between the grains, and those grain actually dissolved here, and based on this dissolution, we have some sort of cementation in other part, because the water, the pore filling water actually will be super saturated with this actually carbonate, and after that it should precipitate the carbonate. The next stage is dissolution seams. Because of the compaction, and compaction, we can see those type of features in the carbonate rocks or a stylolith. And we can see that those type of fracture because some elements are not dissolved, so they remain on that part, and because of that we can see those type of feature in carbonate rock, and they show the chemical or physical compaction. If you look at this graph here, they are from the modern sediments of the, I think from the Bahamas. You can see that based on the depth, we have porosity here at the surface for carbonate rock. But when depth increases, you can see here with the same rock as well as here, we can just see less than 10% porosity. But the sediment near the surface have about or over 40% porosity. And if you look at this part, you can see that because they are more, the limestone are more ductile compared to the dolomite. Based on depth, the limestone compact and they reduce more porosity compared to dolomites. And they are the common feature of the cement fabric of the burial system. We can see the prism at the first stage, we can see the prismatic spar overgrowing marine cement, but after that, we can see druzy, mosaic, and equant spar cement. But after that, after deposition, after high deposition of those or high compaction, we can see syntaxial overgrowth and poikilotopic spar for these rocks. Let's look at two thin section here. They show the early stage of burial Diogenesis system. You can see we have some type of contact between the grains, and some grains actually were broken. And here you can see also here we have compact of sediments. Again, this part shows the solution seams. They show also the chemical compaction of carbonate and also physical compaction, stylolith in carbonate. We can see those type of feature in thin section that shows us we have compaction here. And again, at the last stage of the burial system, we can see extensive calcite cement between grains. And here we can see poikilotopic. It means the last system or the last stage of the burial system. We have another type of Diogenesis, that microtization is not important as, for example, dolomitization or compaction or cementation, but because some of the grains, especially the crust of the grains, attacked by the microbes, and also they create some bores here and filled with the micrite. You can see the shadow of the grains here. And it shows the history actually, or the positional environment of the sedimentary rock for you. But they're not actually important as much as I said, compaction or dolomitization or dissolution in carbonate rocks. One of the important part of the Diogenesis is dolomitization. Most of the dolomites are created by dolomitization of pervious limestone, for example, high Mg calcite, low Mg calcite, and also aragonite. But I don't want to, in this presentation, go in detail for the depositional environment of the dolomite or how this dolomite created, but most of the dolomite are secondary dolomites. So if you look at, I wanted to mention that if we have anhedral type of crystal without shape, we can say this type of crystal of dolomite are non-planar, or if we can see the rhombs of the dolomite, we can say that they are crystalline dolomite or euhedral dolomites, or planar E dolomite, and planar S are actually packed. You can see the packed of the dolomite crystals, and the shape of those are subhedral. Sometimes you can see the shape look like this with straight lines, but sometimes you can see those structural features same as non-planar. This part, actually, this type of dolomite are very important for us because they shows porosity for us. In most of the tidal flats, or sometimes in open marine, we have this type of dolomitization. They are very fine crystalline dolomites. The porosity of this type of dolomite here is very low. And also because the pore throughout is very fine, so the permeability of those type of dolomite is low. And because most of the time in the tidal flat, we have this type of dolomitization, and they are near the evaporite system most of the time, especially in the Middle East, when you have this type of dolomite, if you have a porosity, they fill with evaporite. So this type of dolomitization don't create a very good reservoir for you. But sometimes the dolomite just partially fill the grains or fill the between the grains or into the grains. Actually, look at this one. We have a grains, and because of the microtization, we can see the grains. But after that, it's been leached, and after that, it with some sort of dolomitization, the vugs or the mold actually filled. Look at this image here. We can see some calcite. It's been stained with red alizarin, and with red alizarin, if you stain the dolomite, the calcite get red color, but actually the dolomite don't get any color. So you can see the dolomites here. We can have some sort of porosity here, but in the calcite part, we can't see any type of porosity. But here we have some sort of crystal of dolomite. They are euhedral of dolomite or lumps of dolomite. We have porosity, and actually most of the dolomite reservoir all look like this. So we have large crystal of the dolomite, and also we have intercrystalline porosity. Again, we have another type of the dolomite. They are saddle dolomite. This dolomite show the burial system, and also they show the oil window for us to, and they show that in this part, for example, if you have shale, it can generate the hydrocarbon. And also in this image, you can see the dolomite study under the CL, and you can see the zonation of dolomite, and it's very good actually way to recognize the dolomite crystals. Okay, so let's just tweak the type of porosity. The type of porosity for carbonate rocks or classification of porosity are different. Most of the sedimentologists or carbonate sedimentologists use this type of classification. One of them is based on Choquette and Perry, and one of them is based on Archie here. We don't use actually Archie classification. Mostly for petrophysical work, we can use the Lushov work. So let's just go into the detail of this type of porosity classification. The Choquette, this type of classification for the porosity based on Choquette and Perry, actually, it's related to the fabric and the timing of the porosity development. For example, if it agree, that porosity agree with rock fabric, we say that we have fabric selective porosity. If it doesn't agree with the fabric, if it cut the grains and actually matrix or cement, we say that it's non-fabric. This type of classification is very good for explorationist geologists, because it shows the history of diogenic processes. It shows the hydrocarbon migrations. But for petrophysical studies, actually they don't use this one. But just for carbonate study as a exploration geologist, you can use this one. But if you wanted to categorize the rock types, it's better to use different methods. Because actually, for example, you have in the rock fabric selective, you can have some sort of porosity, for example, 20%, 50% porosity. But actually, when you look at the permeability, they are totally different. For example, one rock with boggy porosity, one rock with intercrystalline porosity, they are different with each other in regards to porosity. In regards to permeability, you have the same porosity but different. For example, you have a carbonate rock with moldic porosity with 20% porosity, and you have also here a dolomite with, for example, 20 intercrystalline porosity, but they show actually different type of permeability. So it's better to use actually Lucia work. Lucia divided the porosities based on two categories. At first, two categories: interparticle and VOC porosities. It mentioned that if we have interparticle, for example, same as interparticle, same as, for example, assume a limestone with porosity. It's between the grains. It looks like if you have those type of porosity, you should actually put that porosity here. If you have other type of porosity, you should put them in these two categories. One of them separate boggy or touching boggy. If you have, for example, moldic porosity, because they are not connected. You have porosity, but they are not connected, so you don't have permeability. So you should put them here in this category. If they have fracture or boggy porosity, you should put them in this part. Okay, let's see some sort of porosity here. For example, in this thin section, you can see the intergrain porosity, intergrain or intergranular porosity. You can see here also intergranular porosity and also fractures. You can see some fenestrate porosity that was created but releasing gas from the carbonate rocks, but they are not connected. So based on the Lucia porosity, you should put them here in separate boggy porosity, but for fracture, you should put them here. For this type of porosity, you should put them in the first category, interparticle porosity. And there are different type of porosity. For example, moldic porosity, intragranular porosity, moldic, and we have some type of WOGs here. So yeah, let me and there are just two type of intercrystalline porosity. You can see we have realms of dolomite here. Between the crystal, you can see the porosity, but look at this actually coarse grain of dolomites, and you can see very large intercrystalline porosity. So based on actually the Lucia work, for especially for rock typing, they use the type of porosity and also the size. After that, Lucia just modified the his classification, and based on the size of the grains or size of the crystals, and also the type of porosity, he categorized the type of rocks and petrophysical characteristic of the rocks. And let's finish with this slide. So this actually graph shows the porosity in the horizontal axis and permeability. You can see that in this part, we have some sort of leach or solution channel or Waggy porosity for carbonates. For example, if you have about 5% porosity, and if you have leach or fractures, the permeability suddenly goes up. For example, we have a formation in Iran. The name is Asmari. That's a very huge reservoir. And if you look at the thin section, you can't see any porosity on that thin section. But most of those porosity comes from fracture. You have low porosity, but you can see very high permeability. And because of the fracture, you can see those type of permeability. But based off the grain sizes, for dolomite, you can see different grain sizes or crystal sizes for dolomite. He categorized the rock types. For example, this part with actually fine crystals of dolomite. You can see if you have, for example, 20% porosity, the permeability is about 1%. But if you have 20% of porosity, but large grain size of dolomite, it's over 1 Darcy permeability. So for Lucia, the thing that important is the connection of those VOC system or pore trout system, or also the size of the grains. So for example, here, maybe we have same porosity with this one, but because of this pore trout system, the permeability goes it goes higher compared to this thin section at this part. Okay, guys, that's all of my slides, and if you have, that's time for question.